Swayam Prabha. Digital India. Educated India.
We're now in the final leg of the discussion of the Benard-Marangoni instability. Let me first summarize what we have done so far. The geometry of the problem is shown on your screen in the non-dimensional variables x, y, z. We have a vertical extent going from z equal to 0 to 1, and we derived the linearized equations for two quantities, which is the temperature perturbation and the velocity perturbation, the vertical velocity component w. Then we assume the normal mode form of these equations, and after taking the normal mode form, we were able to derive two ordinary differential equations, ODEs. That's equation 16. So the f and h are the eigenfunctions for the vertical velocity and the temperature respectively. Then we derived the boundary conditions as well. At z equal to 0, we have the usual no slip and the no penetration condition, and the bottom wall is supposed to be isothermal, so we also got h equal to 0. And at z equals 1, we obtained another condition for f, that is f equal to 0. And with this condition for f, we now have three conditions for the function f. 2 at z equal to 0, and 1 at z equal to 1. The equation for f is a fourth order differential equation, so therefore we need one more condition on f. We also got another condition on h, that is equation 19, and this condition was obtained by assuming thermal equilibrium between the conduction that's happening in the through the fluid very close to the interface, just below the interface, to the convection that's happening in the air above. Now it's important to note that the temperature on the interface is not necessarily fixed at T0, meaning the temperature at the interface just below the fluid at the interface can be different from the value T0 above. Okay, this equation involves a new non-dimensional number called the Nusselt number. We will examine the different limits of the Nusselt number later in the lecture. We now have to derive one more condition at the interface, that's the tangential stress condition. And this is an important condition because this involves the Marangoni stress term. Note that this is a Marangoni driven instability, so this term is expected to become crucial for the analysis. So in the last lecture, we already wrote down the shear stress balance at the interface. Now the shear stress balance involves the surface gradient operator. The surface gradient operator, I will do it on the side here. The surface gradient operator can be defined in terms of the regular gradient del minus n hat of n dot del. And remember that my n is nothing but, it's a flat interface, so it's just the vertical unit vector, n dot del, and therefore essentially becomes Ez dot the del operator. The del operator is nothing but del by del x of Ex plus del by del y of Ey plus del by del z of Ez, and this simply gives me del by del z, that is n dot del, right? So now we also need to connect the surface tension to temperature. We will say surface tension gamma will be gamma naught minus 1 minus delta T minus T naught, and therefore del S of gamma is nothing but minus gamma naught delta del S of t, right? Therefore, del S of t, del S of capital T essentially becomes del minus n dot del of t. Let's evaluate this. That's gradient of t minus n dot, that is Ez, of n dot del, that is del by del z of capital T. Now the gradient of t has three derivatives, that is del by del t of x, del by del t of y, and del by del t of z. The last term will cancel out and we simply have del by del t of x ex plus del t by del y of ey. So that basically goes into my expression here, and this essentially becomes minus gamma naught delta times del t by del x ex plus del t by del y ey. This is expected because the surface gradient is nothing but, for a flat interface, all the variations of the temperature are taken to be only along the flat interface, and there is going to be no contribution from the vertical part, because the surface derivative is only along that flat interface. So the variations of t along the interface are nothing but del t by del x and del t by del y, and that's exactly what enters the surface gradient term. So now we have del S of gamma in terms of temperature derivatives. Okay. So we should also remember that this tau that we have here, this is the tensor tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, and tau zz. One can calculate the use n dot tau dot t is equal to minus t hat dot del S of gamma. This reduces to two parts. Okay, so x component will be tau xz. These are all dimensional. Will be mu del u by del z, and this term is basically tau xz and same as tau zx. This term essentially becomes minus gamma naught delta del t by del x. Again, remember these are all dimensional, and the y component essentially is tau yz is mu del v by del z, and this is minus gamma naught delta del t by del y. So we have two equations here, and what we can do is, let's call these equations as equation A and equation B. So let's take del by del x of equation A, and then we add it to del by del y of equation B. Okay, if we do this, what do we get? Del by del x, that is mu times del by del z of del u by del x plus del V by del Y. That's the left hand side. This essentially becomes minus gamma naught delta. We have del by del x of A essentially becomes del square T by del x square. These are all dimensional quantities, plus del square T by del y square. Okay, this is what we have. So we can further simplify this and say that this quantity here is nothing but minus del W by del Z, right? So we have mu del square W by del Z square is equal to gamma naught delta del 1 square of T tilde. Recall that del 1 square is nothing but del square by del x square plus del square by del y square operator. So this is important result. Let's call this equation C. Now this equation C is at Z is equal to D. Okay. Now we will further say that omega tilde is nothing but epsilon omega hat, and we also had T tilde will be T1 minus theta T1 minus T naught. That's using the definition of theta. If we do this, now we have and we want to non-dimensionalize them as well. So we have mu, the non-dimensional velocity uc, del square w hat by del z square will be minus gamma naught delta del 1 square of theta times T1 minus T naught. Okay, this is what we have. Now this theta is a non-dimensional theta. We have the minus sign because we have T hat. T tilde will be T1 minus theta of delta T. So that minus sign therefore comes in. And we can use the expression for theta. Theta will be theta bar plus epsilon theta hat. We therefore have this is z plus epsilon theta hat, and therefore del 1 square of theta is simply epsilon del 1 square of theta hat. And we also have the expressions for w hat. W hat will be nothing but f of z e power I alpha xx plus alpha yy plus, now they are considering marginal case, so no plus sigma t, and well, it doesn't matter, we can put that in because this boundary condition is independent of whether we are considering the neutral case or not. And theta hat, we took it as h of z e power I alpha xx plus alpha yy plus sigma t. Note that we had written this in terms of whether it's up theta inverted hat or theta theta upside down hat or the regular hat, it does not really matter at this point for this particular case. So I'm not making a big distinction about it. And what we now have is left hand, we want to substitute this, and UC will be nu naught by d. If we substitute everything together, what we have is mu d square f by dz square will be gamma naught delta alpha square of h into t1 minus t naught divided by uc. Okay. And if we substitute the expression for uc, then we have d square f of z equal to 1 will be alpha square Marangoni h of z equal to 1. This is the condition that we obtain. This we'll call it as equation 20. This number, a new non-dimensional number enters. This number ma is called the Marangoni number. Okay. So I want all of you to try and work out the algebra yourself and make sure that all the expressions are correct. This Marangoni number comes out to be gamma naught delta t1 minus t0 times d divided by mu naught gamma naught omega naught. Okay. Mu naught nu naught, or in other words it will become rho naught gamma naught delta d into t1 minus t0 divided by mu naught square. So this Marangoni number depends on the temperature difference and all the other material properties and the geometric property d. And also note that the Marangoni number contains the quantity delta. Delta is nothing but it tells us the sensitivity of the surface tension to temperature. So delta will have units of surface tension to temperature. Now this is the final expression that we have, and I just realized that we have used h for the eigenfunction h for the eigenfunction for theta, but we have also used h when we defined the Nusselt number. So please note that this h here, the heat transfer coefficient should be, maybe we should have called it something else. Let's call it as this is from convection, so we'll call it as hc. Okay, so I should have made it clear that these two h's are not the same. One is the eigenfunction, the other is the heat transfer coefficient. So let's now summarize the equations. Equations and boundary conditions. So we'll start with the equations that we first wrote down. Equation 16. So we have, I'll write down the first equation for f, d square minus alpha square whole square of f is equal to 0. This we'll call it as equation 16a. Then we have another equation for h, alpha square of h is equal to minus f. This is 16b. Let me make sure that these equations are correct. Alpha square of h is, it's not minus f, sorry, it's plus f. A small correction, this is f. So now we have to write down the boundary conditions. At z equal to 0, we have f equal to 0, df is also 0, and h is 0. This we called it as equation 17. At z equal to 1, we have f equal to 0, Then we have minus dh is the Nusselt number times h, and finally the last expression that we just now got, d square of f is alpha square Marangoni number times h at 1. So this we called it as equation 18, 19, 20. Okay. So now we have these equations. Now these are not there are exact solutions for these equations, because we look primarily looking at the marginal stability condition. The general solution of 16a, I will state it without deriving it systematically. Because the derivation is not important, I want to finally show what we're going to get with this analysis. What will be the stability map? The general stability criteria would be, the general solution will be f of z will be a sin h of alpha z, then b cos h of alpha z, then cz sin h of alpha z plus dz cos h of alpha z. This is the general solution. Now using the conditions, what are the conditions that we can straight away apply? We can apply the conditions at 17, that is f equal to 0 and df equal to 0 at z equal to 0. We can also apply the condition 18. So what we have is, using f equal to 0, df is equal to 0 at z equal to 0, and the other condition, which is f equal to 0 at z equal to 1, we can evaluate three of the constants. In this case, we'll evaluate b, c and d in terms of a, and therefore what we get is, we get f of z will be slightly cumbersome expression, sin h of alpha z plus alpha cos h of alpha minus sin h of alpha divided by sin h of alpha multiplied by z sin h of alpha z minus alpha z cos h of alpha z. So we'll call this equation 21. Now we can substitute this f of z into 16b to obtain h of z. We will also employ the conditions we'll also use the conditions h is equal to 0 at z equal to 0 and dh plus the Nusselt number of h is equal to 0 again at z equal to 1. What do we get? We get h of z will be a times c1z cos alpha z. This would be cos h of alpha z plus c2z square cos h of alpha z minus 1 by 4 z square sin h of alpha z c3z sin h of alpha z plus c4 sin h of alpha z, where these constants, I'll write the expression for these constants, but before that let me just say that if you look at these equations 16 and 17, 16 can be written expanded out, it's a fourth order equation. So you have d power 4 terms, you have d square terms, and you have alpha power 4 terms. It's an equation with constant coefficients. You can assume exponential solutions. And when you assume exponential solutions, e power alpha x and alpha z and e power minus alpha or e power lambda z, then you will get basically sine hyperbolics and cos hyperbolics as the solutions, and also you'll get z sine hyperbolic and z cos hyperbolic. That's the general expression for f. Once you've done this, then you get, it's a routine, some tedious algebra is involved, but one can basically apply the conditions at z equal to 0 and z equals 1 for f to get equation 21 that you see on the screen. And the equation for h is a bit more tedious, because now you have to solve for an inhomogeneous equation, differential equation for h, and we can use variation of parameters or method of undetermined coefficients to evaluate this expression. It's a bit tedious, but it is still possible. Now this expression for h involves 4 constants. We'll write down the expressions for 4 constants, where constant c1 will be 4 by 3 alpha, constant c2 will be alpha cos alpha minus sin h of alpha divided by 4 alpha sin h of alpha, c3 will be h of alpha divided by 4 alpha square sin h of alpha, and c4 will be minus alpha square cos h square of alpha plus alpha sin h of alpha cos h of alpha plus sin h square of alpha divided by alpha this is the first term, and then we have another term which is Nusselt number alpha square plus sin h of alpha cos h of alpha sin h square of alpha whole divided by the same thing in the denominator. That's the expression for C4. So we have now basically obtained the expression for f of z and h of z. We still have not used one condition. What condition is that? We still have not used equation 20. That's the condition for the stress, tangential stress condition at the interface. So so we now have two conditions here. So let's basically write down, let's give these equations labels. They have 21, and equation for h of z is 22. So we have substituting (21) and 22 into equation 18, and after some tedious algebra we get an expression for the Marangoni number. We get an expression like this. The Marangoni number is on the left hand side. This becomes 8 alpha cos h of alpha plus Nusselt number of sin h of alpha minus sin h of alpha times cos h of alpha whole divided by alpha cube cos h of alpha minus sin h cube of alpha. This basically is the expression for the Marangoni number at the interface. Just remember, this is it with the assumption that on the neutral curve the principle of exchange of stability is valid, which means that on the neutral curve we anyway don't have any growing or decaying solutions, but we are also not having any oscillatory solutions. So this equation, we'll call it as equation 23. This is equation 23. So what we have managed to now do is to come up with a relationship between the Marangoni number, and on the right hand side we have Nusselt number and alpha. So we can now construct a kind of a stability map. We could have a stability map as follows. We could say I'm imposing a wave of a certain wave number or wavelength, and what we're imposing is on the x-axis, and we want to find out we want to plot a Marangoni number on the y-axis and ask what is the shape of this curve. Now this expression, that is equation 23, gives me the shape of this curve. Okay, what is the shape of this curve? It tells us for every alpha there is a corresponding Marangoni number, and if you are above that Marangoni number for that particular alpha, then you have an instability. Again, remember what was the definition of the Marangoni number? The definition of the Marangoni number, you can see here, I will highlight it here. The definition of the Marangoni number involves temperature gradients. So it involves the temperature gradients or temperature difference across the wall. So I can easily make the flow unstable by simply raising the temperature of the lower fluid. I can also change the Marangoni number by choosing a fluid which has a higher delta, which means that higher delta would mean that surface tension would change a lot more easily with temperature. Small temperature variations are enough to create appreciable changes in the surface tension value. And these changes in surface tension, what it does is it creates Marangoni stresses at the interface and drives a convection. It drives a instability. So if you are below such a curve, then you are in the stable region, and if you are above such a curve, you are in the unstable region. Now note that this particular curve that we have plotted is for one particular value of the Nusselt number. The Nusselt number Nu is some constant that you take. So the approach, one way to make a plot like this is to fix the Nusselt number and choose a value of alpha and find out what is the corresponding Marangoni number. Okay, and then obtain a curve. So you can vary the alpha and then determine Marangoni number for every value of Nusselt number. So you can actually have different values of Nusselt numbers will have different curves. So typically you can expect that the Nusselt number remember is the ratio of convective to conductive heat transfer. It was HL by K. HD by K, sorry. So this is H is here the convective term. Okay. Now if you look at this expression here, expression 19, that's very important to understand. You can look at various limits. Now let's quickly look at this. expression 19 essentially is minus dH is Nusselt number of H. So if Nusselt number goes to 0, meaning if there is no convection to the top, then essentially it means that del dH by dZ is 0. This is an adiabatic condition at the interface, and no heat is getting lost to the surrounding, and therefore because no heat is getting lost to the surrounding, what you have is the temperature. You should expect that it's much more easy to generate temperature perturbations at the interface, and because heat is not getting lost to the surroundings, and as a result what you will end up getting is more Marangoni stress. So this curve that you see here that I'm plotting in the stability chart, you should expect that this curve, the lowest curve will happen for Nusselt number is equal to 0. If on the other hand, if we take Nusselt number going off to infinity, then this would be H is equal to 0. H is equal to 0 is an isothermal condition. Isothermal condition means at the interface, because you can clearly see when Nusselt number goes to infinity, then 1 by Nusselt number goes to 0, you can divide throughout by Nusselt number and you get H equal to 0. H equal to 0 means no perturbations, no temperature fluctuations, at the interface. If there are no temperature fluctuations at the interface, then there are no Marangoni stresses at all. So what we should now expect is that the stability, you can get a series of stability curves like this, or maybe I'll just make a fresh plot. We should get in the stability map, what we have Marangoni number, and this is Marangoni. Remember, this is Marangoni for sigma equal to 0 and alpha. We can get a series of curves and so on. So this lowest curve that is possible, the most unstable curve, you would expect it to occur for Nusselt number equal to 0, and this would be the direction of increasing Nusselt. Okay. So as Nusselt number goes off to infinity, then the entire region in this stability chart, that is for all values of Marangoni number and all values of wavelengths, the flow is completely stable. Okay. Now what I will show you two results. One is an experimental result that was reproduced in my lab, and the other is the actual stability chart that we can obtain numerically. Okay. Now here's an actual calculation directly obtained from that equation that we showed above. The plot of equation 23, the Marangoni number versus Nusselt number, and as expected, you can see that as you increase the Nusselt number, the stability curve moves further and further away up, and the region of stability starts shrinking. Now we can also do an experiment. This is an experiment we've done an experiment where we have taken a heater and heated it to the bottom, and we have thin layer of silicon oil, and if you see the convection pattern, it's not you can see some hexagonal convection, polygonal convection cells. So what is really happening is that the fluid is actually rising from the bottom and then again dipping down, and because there's motion along the interface. So I hope you learned a new interesting phenomena in interfacial flows, the so-called Benard-Marangoni convection. And with this, we will conclude this discussion on this instability. Then we'll move on to other topics in the course. Thank you.